Hi, myself Shubham, and I am starting with a new feature in test benches, that is interfaces. So interfaces are a major new constructs in system Verilog, created specifically to encapsulate the communication between blocks. So consider the example of a full-blown silicon on-chip design in which you have multiple blocks. Now each multiple blocks will try to communicate with each other, and they will have their own wires and pins. Now for example, if there is a module A which want to coordinate with module B, and similarly there is again the module A want to communicate with module B, C and D, so they can have different interfaces so that they can communicate between each other. So in that way, interface provides a good way of modularity, and it's actually helps in design reuse. So interfaces allows a smooth refinement from abstract system level through successive steps down to lower RTL and structural level of designs. It facilitates design reuse, or hierarchical structures that can contain other interfaces as well. For example, if you are considering the example of bus protocols, in which you can have one protocol inside other protocol, and in those examples, interfaces are really helpful, and they can give you different versions of protocols inside one and another. Interface can also be considered as bus, basically, where the whole where each signals and wires and inputs can be considered as a collection of wires, and these interfaces also provide functionalities like tasks and functions, and they can actually do some mathematical computations or tasks, or they can even notice clock edge events as well. Interfaces are full designs when multiple blocks are interconnected, as I said. So interfaces are particularly useful in designs where there's a many to one connection, and one block can coordinate with 10 other blocks, and only just changing the interfaces can be a wonderful experience. So in this example, this interface, there are two variables here, in which one is a bit type and other is a 10 bit 11 bit variable, and that is it can be called as a bundle of wires. So coming to the example, now in this case, this interface is basically logic A, B, logic C and D, and logic E and F, and that's interfaces. Now in the top module, you have just instantiated an interface W, and in with W you can connect the two wires. Now module A and module B are two separate modules. As I said, that they are two different modules which just take input as interface I1. So what here is being happening is that mod underscore A M1 is connected to interface I1, and that is connected to W. So the W is an instantiation of the interface inside the top module, and I1 is the input signal of module A. Similarly, I2 is the input signal of module B. So W is connected to I1 and I2 respectively. So this can be visualized as module A is M1, module B is M2. This is the top module, and interface is basically communicating between the two blocks, module A and module B. Okay. Now this is an example of an ALU interface, which is fitted into the class my ALU, which was earlier told, and you can see that there is a concept of virtual ALU interface. So this is an important because important case of system designs or in test benches, where you can have versions of ALU. For example, if there's a company which generates 2 or 3 different kind of ALUs, then different versions of ALU. So the same class can be used for different ALU versions. You just have to pass that interface to this virtual interface, and hence the connection is all there. So this use of interfaces along with the class gives a great sense of design reusability, which is very important in case of verification, where every now and then a new version of a protocol or a new version of design comes up. So hence virtual interfaces are really important, because if you go with the traditional method of connection of pins, and in that case, even if 1 or 2 pins have to be changed, then the whole design has to be searched for, has to be scanned for, and appropriate connections are remade. But in this case, you just have to pass the actual interface from the top level module, and that's it. The thing is done. So in this case, this is an example of interface. This is an example of interface which has two 8-bit inputs, data 1 and data 2, and this basically generates traffic. So after the constraint randomization is done, which I'll come up in later slides, you have data 1 and data 2 from classes, and the virtual interface's inputs, data 1 and data 2, are given those values. That's it. So it is basically generating traffic, and this traffic is then used as inputs to the DUTs. So that is what done here. So actually you don't have to pass this data 1 and data 2. This data 1 and data 2 can be extracted from the definition to the verification engineers, and you just have to pass this virtual interface, and that will take care of. So you will get to understand this in a greater detail in the lab assignment which we have forwarded this with you, and you can consult that with how the virtual interface is being connected in the classes. Okay. So let's come to interfaces. Clocking blocks. Clocking blocks are basically identifying clock signals and captures the timing and synchronization requirement of the blocks being modeled. So for example, in an interface, if you have 2 or 3 clocking, if you have 2 or 3 inputs and outputs, then the clocking blocks generally give a synchronization synced points to for the inputs and output to be synced with the help of the clocks. So the key element is cycle-based methodology, which enables users to write test bench at a higher level of abstractions. So once a clocking block is defined, you can mark what are the inputs and what are the outputs, and what skews do you basically want. So generally, if for an example, in case of a design, you can have all the inputs sampled at negative edge of clock and all the outputs sampled at positive edge of the clock. In the coming up example, you can see that this is a clocking block in which the default input is skewed for 10 nanosecond and output is skewed for 2 nanosecond. So all the blocks, this block is basically triggered at positive of clock. The outputs are the signal read, write, read, enable, and address, and this signal, this basically overrides the second line, and it basically checks at the neg edge of clock instead of the hash 10 nanosecond of skew. So by this way you can actually override your previous constraints, and hence all the data is being sampled at neg edge, and the read, enable, and address are sampled at positive clock with 2 nanosecond of skew. So you can see that you basically have added a synchronization of all events, and based upon your timing parameters you can do this. In this you can sample the input at and when required, and it is basically driving the synchronization logic which you want to have in your design. Okay. Now we come up to an important concept which are actually used in modpods, and modpods and interfaces are like they go hand to hand, and basically in design you will always have a DUT, you will always have a test bench, and you will have an interface. Now inside the interface you can have modpods where some modpods will be directed towards the DUT, some modpods will be directed towards the test bench. So instead of having multiple wires, multiple pins, you can actually have a collection of inputs in a single modpod and directed toward DUT or toward test bench. Let's look at example in the previous slide. So coming to the definition of modpods, basically modpods provide direction information for module interfaces ports and control the use of task and function within certain modules. So you can also have some tasks or functions with modpods, and like for example, if you can have generating traffic, which will be just for the test bench, and getting the result. Such kind of task or function can be restricted to DUT or test bench depending upon the users users preferences. So that is one thing. So in this particular example, what we have done is that we have an interface INTF which take as the input of the clock, and there are read and enable R2 logic. Then there is a 8-bit logic signal, address, and data. Now you can see that there is a particular modpod restricted for the DUT, and there is a particular modpod restricted for the test bench. In the DUT modpod, there you can see that the inputs are read, enable, and address, and the output is data. So comprehensively you can say that the DUT takes input as read, it takes input as the enable, it takes input as the address, and it receives the output as data. Okay. Now in case of test bench, what it does is that test bench generates the value of as input. So it will generate the read signals, it will generate the enable signal, it will generate the addresses, and the input it will take as from the DUT as a data, so that it actually, you can refer to the previous slide in which the test bench actually generates values and it takes in the result. So coming to the coming to the module DUT. So in this DUT you have basically instantiated interface.DUT. So you can see you are basically using only the DUT mod port of the interface, and that is done. In this case you are actually assigning data of dot underscore if, and you are just saying whether which, depending upon temp1 which temp2 or temp3 will be taken care of, and then you have some codes. In module test bench again you are basically passing that the mod port which was for the test bench in the interface, so that is interface.tb and tb underscore if. So what happens is, in the module top you have a logic clock, and then you have an interface bus if. Now interface bus if have two mod ports, one is for the DUT, one is for the test bench, and respective interfaces are connected to the DUT and the test bench. So in all the internal signals are connected automatically, and in the top module you can say the connections are really limited and very easy to understand as well. So you can consider this is a top module, and this is the DUT basically, this is the test bench, and you have just instantiated an interface. So interfaces will be like this. So inside the interfaces there will be will be for the DUT, and one will be the for the test bench. So these are the mod ports. Okay. Now once the interfaces are done, let's come to an important category of verification, that is constraint randomization. Now we have already discussed what are classes, what are interfaces, and now we are ready to understand how classes and interfaces are connected to DUT, and how values are randomized so that interfaces can connect to the DUT and pass those values. So till now we have discussed the skeleton of verification. Now how the values will be generated, how the constraints are applied, we will see in the next few slides. Okay, so what is randomized verification? Randomized verification are expressions to complex scenarios. They provide flexibility to control dynamically. They can be combinatorial and sequential constraints. Randomness is effective in exploring unanticipated areas. So for example, if you consider the traditional way of verification, where you have to have a set of values. So in case of small inputs like 4-bit or 8-bit, you are restricted that there will be only 16 bits or 16 different values or 32 different values. But in case of signals which are 32-bit or 64-bit or in much larger signals, generating all those values and all those combinations of values are very difficult. So in those cases randomness is very effective, as it can actually approach to the full spectrum of values. So you can have values of negative, you can have values as fractions, you can have values as floating, you can have values as 0. So these values will be helpful in complete verification of the DUT, whether the DUT is functioning correctly in all the scenarios, whether it is showing an error message, whether it is giving a warning, whether it is giving a note, whether it is generating a result or not. So in all these four circumstances, a randomness approach is the most effective way to verify the DUT functionality. So you just have to see whether your specification manual, what constraints are they applied, whether that is supposed to work for negative values, whether that is supposed to work for fraction values. So those constraints need to be studied well before, and depending upon those constraints, the class is written, and once the constraint is written, the randomization takes place in that way, that such that only those valuable values are generated which the DUT are supposed to take. After that, once the correct values are provided as input, the DUT has to give the output, and that can be checked to see whether the sanctity of the DUT is maintained or not. So random constraints, there can be constraint driven test generations. Constraints can be of three types. There can be specification driven constraints, as I've told you. Then there are default preference constraints. Some constraints need to be default controlled. Like if there's a 8-bit number, you can't pass on like an integer number to that. Then there are test and config constraints as well. So every class has a virtual predefined function randomize. So randomize is basically when in the previous example you can see that there is rand bit data 1, rand bit data 2. So once you call the randomize function on the object of the class, only then the randomization will happen, and it is not 100% sure that randomization will take place or not. So we'll come to that in the next few slide. So randomization function is there. Then various constraints need to have up to be applied to have the correct randomized value, considering the divide by zero example in the previous slide. So in the previous slide, if you're considering for an ALU and you have to see whether deviation is performed correctly or not, then you need to have that constraint of divide by zero, so that value is never generated. The denominator can never be zero in this case, because if that is zero, then that will not behave normally, or will not perform the verification correctly. So another case can be to find whether the result can be there for inputs which are negative values. Other constraints may include certain specific ranges like factorial, like fraction numbers, and all those cases. Okay, so in this example, there is a class simple, and there's a class simple in which you have randomized integer variable where there are two constraints C1 and C2. The first constraint is that var should be less than 100. The second constraint is that var is greater than 200, and that is n class. Now in the initial begin, you have created an object of simple, and you just call object.randomize. Now if the simulator is not ready to randomize that value, then it will show this randomization failed. So in this you can see that if randomization failed, the constraints are infeasible and the random variables retain their previous values. In the following example, for the first randomization call, there is a solution. When the constraints are changed, the randomization failed. Simulation results show that after randomization, the random variables hold their previous values. You can have multiple randomized calls within the same test bench. So at one time you can have a new value, and at the other time you can have some other random value, and in this way a whole test suite is generated with around like hundreds or 200s of different values, and through that the DUT is regressed, so that you can say 100% that verification is done here. Okay, the best feature of constraints is that they can be overridden at any point of time. You can override the constraints from the extended class. You can override the constraints from the test bench as well. So, like if you have to do some negative testing, you can actually override the constraint, the original constraint of the class, and you can actually override the original constraints of the class, or you can actually modify the constraints of the class. So that flexibility has been provided to system verilog by the system verilog for the verification engineers. So in this case, for example, if you consider the case that you have to have only an odd number or an even number, so that constraint has been added, and only even number will be generated in this case. So this kind of flexibility is provided by the constraint randomization. The next is the pre-randomized and the post-randomized functions. So these are basically hooks to for settings of initial values. Now, like for example, unless and until the randomized function is called, so just before the randomized, pre-randomized will be called, and just after the randomized, post-randomized will be called. So these are for the hooks for setting initial values, whether you want to have some data checking or some data warehousing need to be done before calling the randomized. So, and also in this case as well, the pre-randomized and post-randomized functions can be overridden from extended classes, or can be overridden from the test bench itself. One more thing is that once the specification is read, the engineers are supposed to develop a verification plan, and in all those verification plan, you